In this set of videos, we're going to cover section 6.1 through 6.4, covering generalization and Leibniz rules, which are different rules to be able to use within proofs in predicate logic. So in fact, these videos are really going to focus on section 6.1 and 6.2. And the learning outcome for section 6.1 is that you will be able to use the meta-theorems spec for specialization and gen for weak generalization in theorem calculations or proofs in predicate logic. So in predicate logic, we're going to be able to use these meta-theorems directly in our Hilbert proofs. And then we'll cover section 6.2, and within this section, you'll be able to identify the difference between BL, WL, and SL, which stand for Boolean Leibniz, which is our rule of inference, weak Leibniz, which we'll learn what that is, and strong Leibniz, and we'll also learn what that is. And then you'll also be able to use both weak Leibniz and strong Leibniz in theorem calculations or proofs in predicate logic. And these are going to be most helpful in equational style proofs. We will also cover section 6.4 in class, which is essentially to use an alternate method of equational proof. So we will use the same equational style proof as we did before, but we're also going to introduce an alternate method to help us to write other kinds of proofs in predicate logic. Okay, so now that we are getting into theorem calculations or writing Hilbert and equational style proofs in predicate logic, we need to review a few things that we can use. So recall when we studied post theorem, which is the completeness of Boolean or propositional logic, we discovered that post theorem allows us to simply use any tautological implications as derived rules of inference. So instead of having to prove some kind of relative theorem to be able to use it, we could just simply justify through tautological implication the use of truth tables that this is a relative theorem or derived rule of inference that we can apply within our proofs. And this corollary simply formalizes that statement. So it says that if gamma proves well-formed formula A1 through AN, and A1 through AN tautologically imply B, then gamma proves B. So essentially, if we have any of these statements written in our Hilbert proof, and we can use all of these assumptions and know that they tautologically imply B, then we can use this completeness or post theorem or tautological implication, all of those different annotations, to be able to write B within our Hilbert proof. So essentially, to summarize, we can use any tautological implication schema as a derived rule of inference in our proofs. And that we did at the end of the first half of the course in propositional logic. So on the midterm, for example, you were able to use truth table arguments on the side of your page to be able to incorporate into your proofs. Or you were able to use truth table arguments entirely to prove something as well. We need to be a little bit careful as we move into predicate logic and using tautological implication. So for example, we do not know that predicate logic is complete. So we don't have this same understanding of completeness within predicate logic just yet, and we'll discover at the end of the course that it's both complete and incomplete at the same time, and we'll go through what I mean by that. But we can use post theorem, which is why we're using this terminology, recalling that from last class, tautological implication within predicate logic is simply taking the abstraction of a well-formed formula in predicate logic and defining tautological implication in the same way as for propositional logic. So we're going to be able to use tautological implication or post theorem in our proofs in predicate logic so long as we're only concentrating on the actions of the connectives and not worried about any of the new non-Boolean symbols that we've added. So we'll see examples of this later on, but the one thing I want to draw your attention to here is that as you look through proofs within the textbook, for example, oftentimes the annotation is going to identify tautological implication. So this means that they've applied Post's theorem on simply the connectives by abstracting the rest of the connectives. And we can look at an example of this in class for sure. So that's one thing that I want to draw your attention to in terms of proofs within predicate logic. The other thing that we've talked about is this notion of equivalent logics. So what do I mean by that? So two different logics are equivalent if and only if they have the same absolute theorems and relative theorems. So we talked about this a little bit when we were comparing the logic we defined, in particular Boolean logic, with the logic that you're kind of used to in Math 1019. And we talked about one of the first rules you learned in 1019. One of those main rules that you recognize was modus ponens. And I think I mentioned to you in class that it turns out that it is equivalent to define our logic the way we did with the two rules of inference, Équivalent and Leibniz, and to define it using only modus ponens. So we can prove, and it is proved in chapter 5, that these two different logics will have the same absolute theorems and relative theorems, and so they are equivalent. So let's represent logic 1 by our now predicate logic with primary rules EQN and Boolean Leibniz. And let's let logic 2 be predicate logic with one primary rule, modus ponens, right? So this is that if we have A and if we know that A implies B, then we can conclude B, right? So that's what the modus ponens rule of inference says. So, using a couple of lemmas, we can show, and it is shown in chapter 5, that these two logics are in fact equivalent. So, the first lemma says that Post's theorem holds in logic 2 for finite gamma. So here we call Post's theorem is the completeness of propositional logic. So here we're only looking at the definition of tautological implication, focusing on simply the connectives, getting rid of any non-Boolean symbols. So we can prove using modus ponens that Post's theorem holds. And then you can also prove that logic 2 has EQN and Boolean Leibniz as derived rules of inference. But then as soon as that's the case, since we know in logic 1 all of the absolute theorems or relative theorems are derived from here, in logic 2 we can derive all of the same absolute theorems and relative theorems, and vice versa. We know that modus ponens is a derived rule from EQN and Leibniz, and hence Boolean Leibniz, and so we can derive the same absolute theorems or relative theorems. So the meta theorem is essentially combining these lemmas, tells us that logic 1 and logic 2 are equivalent. The reason this is helpful really is in the proofs of some meta theorems that we'll talk about in the next video, in particular weak Leibniz. We won't actually go through the proof of this in class, but it is in the textbook, and it uses the fact that they're working within logic 2 to prove that meta theorem. So up here, I guess we should also identify different logics are equivalent if they also have the same meta theorems. Okay, so that takes care of the introduction to these videos when we're talking about just getting into our proofs. Next we'll look at some tools to be able to use within our proofs in predicate logic.